Right, let's make a start. So, hi everyone. Thanks so much for being here. I'm very pleased to introduce Dr. Jacob Lustig-Yaeger. So, Jake did his undergrad at UC Santa Cruz before moving here to do his PhD in the astronomy department. And so we overlap for most of our PhD, I think. But then Jake went off to Johns Hopkins to first do a postdoc, and then he's now a permanent staff scientist there. But fortunately for us, Jake lives in West Seattle, and so it was very easy for him to come here today and talk to us about his work. So they say Jake is trained as an astronomer, and a lot of his work in his PhD was sort of thinking about how do we make sense of exoplanet observations. And so recently he's been very involved with efforts with the James Webb Space Telescope to characterize rocky exoplanets. So for those of you that don't know, if you want to use like the James Webb Space Telescope, there's a proposal process. So you make an argument for why you want to look at this star, this planet. You write a proposal to explain exactly how your observations are going to work and what exciting things you're going to discover. You submit it to a review process, and then your proposal gets rejected because it's like a 10-to-1 selection, like oversubscription rate. But Jake has been incredibly successful. He is like the PI on this very large program, 250 hours of observing time to look at rocky exoplanets. So I'm sure he will update us on how that is going. But also, one thing I really like about Jake's work is that he's not afraid to kind of take his toolkit and apply it to other interesting problems. So he's done some interesting work thinking about like how do we test the geologic carbon cycle on exoplanets. He's involved with the Da Vinci mission to Venus and thinking about how we can characterize the surface of Venus. He's done some recent work on sort of small bodies in the solar system, so I'm sure he'll be telling us about some of those exciting projects. So with that, I'll turn it over to Jake.
Awesome. Thanks, Josh. It's fantastic to be here. Can you all hear me okay with the mic? All right. Fantastic thumbs up. Well, it's so good to be back and living in Seattle, like Josh said. So without further ado, I've got sort of a large amount of material I'm going to try to cover, weave together somewhat artistically into a coherent narrative for you all. And so let's just jump right in. So the bulk of my work focuses on the characterization of exoplanets and understanding their atmospheres, like Josh said. And this field is just growing at an astronomical pace. Since the first discovery of exoplanets in the mid-90s, now we have, we have well over, or just over 6,000 known exoplanets, and this number is just going to continue to grow as NASA puts more missions in space that increase our capabilities at finding exoplanets, thanks to mostly these four detection techniques shown here. And naturally, my career is motivated, like so many, and by this question, are we alone? With this massive pile of exoplanets, this population, we have such a unique opportunity to search for life beyond the solar system. And so throughout this talk, I'm going to sort of highlight a few research themes that I try to center in my work. And so the first thing, I use space telescopes, like Josh was saying, to observe exoplanets and infer their atmospheric compositions. I also really like to use solar system as a lab to ground truth exoplanet models, methods, and hypotheses. And third thing I like to do is use the population. I think this is where the power of sort of exoplanets comes to the fore, is we can use the massive number of exoplanets to answer questions that are just impossible to answer from single objects alone. So in this talk, I'm going to cover sort of three sections that are only loosely connected through those themes, but we'll first talk about small bodies and specifically work that I've done with my colleague Kathy Mont at NASA Goddard on revising the D/H ratio of the comet 67P, was the focus of the Rosetta mission. Next, we'll talk about small planets, in particular Venus. I've worked on several Venus projects, but I'm going to focus on the Da Vinci mission and some of the work I've done refining the requirements for the cameras to study the surface. And we'll end with a discussion of exoplanets and ongoing work to search for rocky exoplanet atmospheres with the James Webb Space Telescope. All right, so let's jump right into the first section here. So comets play this sort of amazing role in our understanding of the formation and evolution of the solar system. They inform us on the composition of the giant planets and their moons, as well as being these pristine building blocks to the record of conditions during the early stages of the solar system, and form the volatile inventory of the inner planets in the solar system due to their perturbed orbits. And there are a bunch of different sort of regions where you might find comets, a variety of different orbits. So we're going to be talking about this comet 67P, which is a Jupiter family comet. Has a 6.5 about year orbital period around the sun. Other comets like Halley's Comet are further out, coming from the Kuiper Belt, and have like a once in a century close pass, a perihelion passage of the sun. Still yet, some comets like Siding Spring are further out in the Oort cloud and have a chance a trip into the inner solar system once every million years or so, and we get lucky to catch these. And even more recently, there have been interstellar asteroids or comets passing unbound by the sun and passing into the solar system and sort of leaving to never return again, composed of sort of building blocks of extrasolar systems, a really interesting new avenue to studying the diversity of planetary building blocks beyond the solar system. So, of course, with comets, we're familiar with their two tails, the plasma tail and the dust tail, and given this characteristic look that we all kind of know and love. We've got the nucleus in the middle and the surrounding coma, the inner region. And so the Rosetta mission was set out to rendezvous with this comet 67P. I'm not really going to try too hard to pronounce the full name of this one, but it followed the comet, it got an orbit around the comet, and followed it into the inner solar system as it did its perihelion passage to measure the increase in activity from the icy surface as it was warmed, map its surface features and its composition. You may also be familiar with its Philae lander, which kind of ricocheted around the crater rim and came to rest in a sort of shaded region, but it still was able to take some amazing pictures right up close of the comet's surface. I think it even measured some seismic activity on the comet. So it was still a success, sort of despite tumbling around in its chaotic landing. But the D to H ratio inferred from this comet by the Rosetta mission has been confusing. D to H in water varies with temperature in the protosolar nebula, and a high D to H implies, like this comet was originally found to have, implies a very cold formation temperature, and it should correlate with high nitrogen and carbon monoxide abundances. But the D to H for 67P doesn't agree with other Jupiter family comets or its own nitrogen or carbon monoxide abundance. So this is kind of a mystery for the D to H ratio that was obtained. So my colleague Kathy Matt set out to use the full mission data set to study comet 67P, and basically, the Rosetta mission had this instrument, the Rosina double-focusing mass spectrometer, which was used to basically sniff the coma material as it orbited around the comet. As the comet came into the inner solar system, became more active and was heated. So determining the D to H ratio requires separating these overlapping peaks for a given species. It's maybe a little bit difficult to see, but each of these peaks in this mass spectrum correspond to a different species. We're really interested in this peak here from HDO. That way we can access deuterium and compare it or back out the D to H ratio of the materials coming off of the comet. But there's this triple complex here because it's neighbored by H217O to the left and this mystery species, the hydronium H3O on the right, basically forming just a complicated mess to disentangle. So I actually brought some Bayesian statistics techniques that I use to study exoplanet atmospheres to help disentangle these overlapping peaks and provide like a robust statistical analysis of our uncertainties given sort of the ambiguity that results when you have these overlapping peaks and sort of open questions about what species may or may not be there. And then we ran this model on the full data set shown here on the right, where about 1,000 days of data were taken, and there's a massive amount of variability there in the D to H. The salmon bar kind of shows the measurement that was made from just a few, the inference of D to H was made from just a few measurements by prior works. And so really, Kathy Mount had the great idea to use the full mission data set and investigate sources of variability and try to really pin down the D to H ratio. So one recent revelation that's helped contextualize the work we've done is that the Rosetta mission measurements are local and are only observing volatiles near the spacecraft. So we kind of thought about 3 different regions: the sort of pre-perihelion approach of the comet as it's heated, the perihelion passage, so that's the salmon box labeled 3, the perihelion passage labeled 1, and then the post-perihelion for 2, labeled 2 here. And so past work showed this intense southern activity around perihelion, and then post-perihelion you get the redeposition of materials in other regions, and then when it comes around later for 6.5 years later for its next perihelion passage, you have sort of the reactivation of those materials. It kind of demonstrated this cycle of materials being sublimating from the comet and redepositing on the surface. So you get this extended source of gas from the sort of this process. And a critical thing here, I'm going to try to walk through this diagram. And so, keep in mind, I'm an exoplanet astronomer here, so I'm going to do my best walking through this process, and it is kind of small and complicated. But the key is that lab studies have shown that HDO that we're targeting here to understand the composition and how much there is, it preferentially sticks to dust, more so than sort of just not heavy water, H2O. So there is this process measured in a lab. It's sticking, the heavy isotope is sticking to the dust. And so to sort of set the stage here for this process, we have the exposed nucleus here in sort of the first panel, where we have water ice, this sort of blue region, and then the gray blobs are the dust. And so we have the water ice from the nucleus sublimating, exposing some of those dust grains at the top. And then in B, we have the HDO and other volatiles sort of sublimating from this reservoir and preferentially adsorbing to the exposed dust surfaces. Then, panel C here, we've got additional, slightly enriched layers of HDO forming on top of that already enriched layer. And then panels D, E, and F sort of map to these 3 phases of the comet's orbit on the left here. So in D, the dust cycle sort of for the comet begins with enriched water layers. When the increased activity begins to sublimate the increase. Getting confused here just by my own slides. But you've got the release of dust, the sublimation of the enriched HDO into the coma, increasing the D to H ratio of the measurements that the spacecraft is making. That's sort of the gist of it. The dust redeposits onto the surface where the process can repeat. This is sort of the model picture that kind of comes in from the context of previous work that looked at this dust cycle and helps to explain the measurements that we made. So basically, by looking at the full mission data set, we find that D to H varies with these 2 factors. The type of dust, whether it's sort of the old dust versus the new dust, and the distance from the comet. And for example, here in phase 3 here, when we're reactivating this old enriched in D to H, in HDO old dust, we have an intense amount of correlation between the D to H ratio and the distance from the comet here. Whereas in phase 2, we can see a more stable D to H ratio is obtained after perihelion passage. So we set out to figure out if we could find a time and a place where the dust loses its ice and no longer influences the local coma. And that would be where a more pristine D to H ratio of the reservoir of HDO would be found. So here we're basically looking at the post-perihelion points in purple tend to have a lower D to H ratio and less variability, particularly further than 120 kilometers from the nucleus. So this is where we find a stable isotope ratio. So having sort of understood the process and measured the stable D to H ratio, we kind of come back to the context of the D to H relative to other bodies in the solar system. And now our revised D to H ratio does make more sense in context with the implied nitrogen and carbon monoxide abundances. And it also places 67P in line with other Jupiter family comets' D to H ratio. So reopening the possibility that the Jupiter family comets could have contributed a significant fraction of Earth's water, which is kind of the astrobio context of the cometary D to H ratios and the origin of Earth's water. I'll note here, sort of before we move on, Venus's intensely high D to H ratio, just because that will play a little bit of context in a second. But now we have a revised D to H ratio for comet 67P that sort of makes sense in context with the other evidence of Jupiter family comets and comet 67P. All right, so with that, we'll move into the second phase here of the talk, and where we'll switch gears kind of entirely and talk about Venus, in particular the Da Vinci mission and the observations that it's intending to make. So Venus has become an awesome astrobiological target because of the possibility that it once may have been a habitable ocean-bearing world in the past. So despite its current hellish environment, one line of evidence of this is its enhanced D to H ratio, implying a large amount of water loss. Now, whether that water was in ocean maybe billions of years ago is an open question that requires more measurements on Venus. Over time, it could have lost that water, and so perhaps Venus sort of tells the story of the life and death of a habitable planet. So why go to Venus now? So sort of already said part of this, but Venus informs our understanding of how stellar evolution governs climate. It also holds clues to how stable habitability may have been in our solar system and beyond, and it's our ground truth as we move into understanding exoplanets, particularly starting with sort of highly irradiated Venus-like exoplanets. So we need a mission, in the near term to sort of put this Venus into context and be able to sort of tell the story of the Venus's history. So the overarching goal of the Da Vinci mission is to provide a definitive new understanding of Venus to reveal the extent of habitability in our inner solar system and beyond. And we really can't properly model Venus's climate without new in situ quantitative chemical measurements and compositional imaging that Da Vinci will be prioritizing to sort of answer these open questions about Venus's habitability over time. So Da Vinci is going to have a series of measurement capabilities. It'll have a remote sensing phase in orbit from flybys. It'll also have this descent probe that will make measurements from the very top of the atmosphere down to the surface, measuring the whole atmospheric column on its way down and imaging the surface from beneath the clouds. So it has a really interesting concept of operations, sort of centering in this awesome descent probe. And so the Da Vinci instrument suite looks something like this, where most of the instruments are housed in the descent sphere that'll make its way down to the surface, where it's not going to last that long, but it'll make critical measurements, which it'll relay back to the spacecraft. That spacecraft also has a couple of instruments, including this visor imager. And so I've worked as an astronomer on the two camera instruments, and particularly what kind of science they'll be capable of doing. And so we'll start here with the Vendy instrument. This is the Venus descent imager, and so we're looking here on the left at a kind of map of its descent profile, where it'll be conducting a bunch of science on the way down. And so Vendy is really cool. It will be downward pointing, peering through this transparent sapphire window at the bottom, and it'll use high-resolution near-IR imaging to map the 3D topography and composition of Alpha Regio, which is where they're targeting, ending up, and with topographic resolution up to sub-meter scales. So I focused on what it is that the camera will see and whether it'll be able to distinguish between different sort of surface compositions that it may be looking at. And so to talk about this, I'm going to flip to some work that I've done in collaboration with the Avengers group. And this Avengers group stands for Analogs for Venus Geologically Recent Surfaces. And they're this international collaboration connecting mission teams, broader science communities, to provide a comprehensive framework of terrestrial analog sites. So most recently, this group traveled to the Canary Islands, to La Palma, where there was a recent 2021 eruption, to make pristine samples of the lava flow. So unfortunately, I didn't go on this field expedition. I would have really loved to do that. It didn't really make sense at the time. But this is the lead of Avengers, Piero Dencheco, who is seen here very excited on the lava flow here. And here's an obligatory picture for the geologists in the room of the lava flow. Yeah, I really wish I was on this trip. I think being able to show pretty pictures is very cool in a talk, and I hope to be able to go on a future field expedition. But fortunately, they came back with samples, and so they made a few different measurements of samples. And not being a geologist, I'm going to sort of leave these up to you to appreciate the sort of visual characteristic qualities of them. But what I was really excited about was, of course, a graph of the visible near-IR reflectance spectra. And so this was kind of where I came into this project. And in collaboration with the Avengers team, I was provided with these measurements of the reflectance spectra, where I integrated them into my radiative transfer model to figure out if we could sort of distinguish between these different measurements using the different surfaces using the Da Vinci Vendy camera. So you can see here the two imaging bands that the Vendy instrument is planning to observe in, right here with a narrow band filter at 1 micron and a broader band filter that overlaps with that but also extends to shorter wavelength. And so what I did was I built a sort of custom radiative transfer retrieval code built off of the code I developed during my PhD here in the astronomy department with Vicki Meadows. And I built this specifically to work with the Vendy descent imager, which has this unique, only 2 photometric band measurements, but imaging the same surface as it descends through the atmosphere below the clouds. So I simulated this downward pointing geometry, different altitude as the sphere descends, and to mitigate issues associated with absolute calibration, we intend to fit this sort of color magnitude-like descent profile to infer the reflectance spectra. So here we're looking at a ratio of the 2 bands' intensities on the y-axis and the intensity of the broadband radiation observed on the x-axis. I think that this figures from the concept study report. I think the axes are labeled a little bit wrong, but nonetheless, basically you have 3 different materials that have these characteristic descent profile curves, and we want to basically figure out with the measurement precisions expected, can we back out the rough reflectance properties of these different surface types. And so here's an example of the simulated Vendy data using a model for the Vendy camera and sensitivities. Here simulated with a signal to noise of 30 expected. That's sort of the nominal baseline signal to noise that we kind of came up with from our work with the Da Vinci mission. And we want to figure out how well we can back out the reflectance properties of the surface. And so each sort of colored dot here is one of the different surfaces, and we simulated 3 altitudes at which we took imaging. So in reality, the Da Vinci mission will take way more than 3 images at 3 different altitudes on the way down, but we kind of wanted to baseline this for like the threshold mission, the sort of minimal number of images that the Vendy could get away with taking to sufficiently meet the objectives. And so we fit these with a Markov chain Monte Carlo code and infer a range of models that sort of fit these descent profiles, each with different surface reflectance properties. And so to figure out how well we did here, I'm showing the reference spectra that were measured in the lab, and on the right, histograms of our posterior probability distributions for the surface reflectance that we infer out the other end of this problem. We're also fitting for the opacity of the clouds, so characteristics of the atmosphere as we descend through the atmosphere, imaging the surface. And so I'm just going to flip this around here. We're looking at the same plot that was on the right here, but retrieved surface albedo and the relative probability. These are just histograms of our constraints. And kind of crudely, just looking at the separation between these, we can see that they are well-separated peaks, but in particular, the lightest and the darkest measurements from the field are distinguished at extremely high confidence, sort of bolstering our confidence that we will be able to distinguish between sort of oxidation states from surface composition. So I should say that this experiment, each of these measurements you can think of as like a single pixel or a sort of region on the surface that's been observed at many different altitudes. And this sort of represents the analysis you'd be able to do for each pixel in the image. So you could imagine sort of backing out the retrieved surface albedo for whole regions. All right. So previous work has shown that we can also distinguish between granite and basalt, and heavily altered basalt and fresh basalt. So I think, within 0.1 change in surface albedo, you'd expect to be able to retrieve that difference at about a 3 sigma confidence, but something like a 0.3 difference in albedo, you could get at a more like 9 sigma confidence. So that is very reassuring for the success of the Vendy mission and instrument. All right, so we'll flip back to the instruments that Da Vinci will have, and now we'll talk a little bit about the visor instrument. So this will be imaging the day and night side of Venus during flybys. So again, this is the part of the spacecraft that stays in space will be relaying comms back to Earth, but it'll also be doing dayside mapping in the UV of the clouds and nightside imaging in the near infrared of the surface. And so this nightside imaging will use 3 independent near-infrared bands, one to correct for scattered light, another to correct for clouds, and the third to measure the thermal emission from the surface that is emitted through the opacity window at 1 micron. So the work that I did was focused on what exactly we'll see to try to confirm that visor will be able to constrain variations in surface emissivity and its correlations with different surface geology at regional scales. And so this work kind of proceeded a lot like the Vendy work, but instead of talking about that, I'm going to sort of flip and talk about how we understand the surface of Venus from these night side observations. Because the remote sensing of the night side of Venus is a sort of a challenging, incredibly challenging endeavor. It's extremely difficult from the ground and in space due to just the contrast between the daylit crescent on Venus and its night side. It's many orders of magnitude in brightness difference, so you have to not observe any of the daylit crescent and capture just the night side. So you need good spatial resolution to be able to do that. And sort of the most vivid description of this, how the physics of this works, actually comes from this little bit weird, creepy quote from this guy, David Allen, that he said, we're viewing Venus through a net curtain. The uppermost clouds form that curtain, and by day reflect sunlight back to dazzle us. By night, however, we become voyeurs, able to peep into the backlit room behind. Definitely a creepy quote, not something that like somebody would publish in their papers these days, but it does kind of perfectly describe how it is we're able to see the dayside surface when you're not lit by the immense reflection from the clouds. This thermal radiation is able to stream out of the atmosphere, even through the thick sulfuric acid clouds, both because of a difference in scattering properties in the forward and backward direction of the Venus clouds, but also because of that contrast, the ability to see that small amount of light, even just when you don't have that day side contaminating the observation. So this gives you remote sensing capabilities to study the deep atmosphere and surface of Venus. And there's been this interesting timeline of Venus night-side window discoveries. And so this is where some additional work that my colleagues and I at the Johns Hopkins Applied Physics Lab did to sort of advance our understanding of Venus night-side science. So Allen and Crawford in 1984 first discovered that you could even study the surface of Venus, or the lower atmosphere of Venus, through a night-side opacity windows at 2.3 and 1.7 microns. Then, in 1990, Galileo did a Venus gravity assist flyby and helped to confirm it. It made some serendipitous observations during the flyby that helped confirm the existence of this 1 micron opacity window. And this has been used extensively. This is the one that the Da Vinci mission will use and the Akatsuki mission uses, and it just is used widely. Then Cassini did a Venus gravity assist flyby on its way to the outer solar system in 2000, where it did more observations and helped to confirm an even shorter wavelength opacity window into the lower atmosphere at 0.85 microns. And then Parker Solar Probe in 2020, which is a heliophysics mission studying the solar corona, observed thermal emission less than 0.78 microns, the shortest opacity window yet. So this was just a beautiful serendipitous thing that continues to happen with Venus flybys. It's sort of the best, cheapest ticket to the outer solar system is to do these flybys of Venus to change your orbit. And it's great that the cameras are on during those times so we can get Venus science done. So the Parker Solar Probe mission had this wide field imager for solar probe, or this WHISPER instrument. It's used to study the solar corona, and so it has these 2 cameras. One, the inner one is looking typically closer to the sun. The outer one, they slightly overlap, is looking a little bit further away from the sun. But it's never really looking right at the sun. It's studying the faint solar corona. So they're very sensitive cameras. You'd think studying the sun that it's supposed to be looking at something very bright, but really it's doing its best to not ever look at the sun and to instead image the corona. And so during the flyby in 2020, they obtained the image on the left, and then during 2021, another flyby obtained these 2 images and several more images on the right. And you can see here they've imaged a very similar region, and there's sort of dark patches and light patches that sort of remarkably align perfectly with the known elevation map of Venus from Magellan. And so here the dark patches correspond to the image on the right on very high elevations, the highlands that are colder, that emit less light, and the bright patches in the WHISPER images correspond to the lowlands that are hotter and emit more light. And so another thing about these images is that they look exactly like those from Akatsuki. So immediately we kind of knew from these serendipitous images that Parker Solar Probe had observed the surface of Venus, but its cameras operate at completely different wavelengths than had been used to observe the surface of Venus before. So a fundamental question that really we wanted to answer here was, is this optical emission at the red end of WHISPER's response function, in the band from a new atmospheric window? This was sort of the exciting hypothesis. And then, or is this 1 micron emission that is leaking into the band that they are supposed to be observing in? So this is kind of like the null result hypothesis. And so we set out to investigate this. And so I took the Venus model that I was using for my work with Da Vinci and extended the wavelength range down into the optical to see how much light is being emitted in the optical on the night side. And from here we can see these sort of known opacity windows at 1 micron and 1.1 microns between these CO2 bands. It looks like there's just nothing in the optical at the whisper bandpass. So if we zoom in there, we see, okay, wait, there's a little bit of something there. It looks, orders of magnitude less intensity, but it does sort of bear this characteristic drop-off in flux that we expect on the wean tail of a black body radiator. So we took this model and compared it to the instrument response functions of the whisper instrument. And this figure from Wood et al. 2022 shows now the log of the Venus model radiance dropping off like a cliff into the optical, and then the whisper response function. So it's sort of this balance between being on the edge of the camera's ability to detect and really low intensity radiation coming from Venus. So when you convolve these two, you get these wavelength dependent predicted count rates. And so then this is basically what makes it to the detector, which then absorbs or measures the amount of light. And we're able to map this to the measurements we made from these whisper images and found that the thermal emission model in the optical is extremely consistent with the brightness in the images measured from the whisper camera. So this was almost all we needed to convince ourselves that we were indeed seeing emission from a new opacity window in the optical. We did a few more tests to make sure there wasn't a light leak in the instrument using background stars, but we didn't quite get the right, there's an excess of flux in the whisper images, but by and large, this was extremely consistent with what you would expect from a 735 Kelvin surface emitting through the Venus atmosphere. And so got very excited that here we're looking at the spectrum of Venus's thermal emission in brightness temperature. High temperatures tell us we're probing deep in the hot lower atmosphere of Venus. And so you can see these known opacity windows here, in the near infrared. And then you can see this broad opacity window in the visible, suggesting that sensitive enough cameras, perhaps on future missions, could be used to study the Venus surface across this broad wavelength range. So the final thing we did here was to construct a full image model of the images that Whisper made. And so I'm going to sort of walk through a progression here. And we'll start here with just one of the Whisper images, the third in the series from this 2021 flyby. So we ran a grid of these radiative transfer models and mapped them to the image and wound up with this prediction based on our thermal emission calculations for what we think Venus would look like. It's noticeably darker. Its limb is darker than the center of the disk instead of being brightened. And so we developed we fit the residuals from those two with a polynomial in the cosine of the emission angle. We're pretty sure what this is night glow from oxygen, which is emitting, known to emit from the upper atmosphere of Venus, and it is right in the middle of the Whisper bandpass. So no specific ability to distinguish this from the Venus thermal emission other than its dependence on the emission angle here being entirely different from the angle dependence of surface thermal emission. So with this night glow kind of simplified model, we add the thermal model together with the polynomial model for the night glow, and we end up with a pretty darn good reproduction of what this image looks like. And the residuals are pretty low. There are still some residuals here which are small, but could be due to a handful of factors like cloud opacity variations, like if there are thickness variations in the clouds, that could affect this a little bit. Variations spatially in the night glow across the disk could create this too, or potentially surface emissivity variations due to surface compositional differences could also drive these type of variations, but these measurements have no ability to disentangle those effects. So we're kind of left with this interpretation that these whisper images are best explained by surface thermal emission through the thick atmosphere of Venus in a new opacity window in the optical with this overlying air glow, like night glow component from oxygen that's present across the entire disk of Venus in this bandpass. And it's strongly limb brightening. So with this sort of picture of the night side windows in mind, sort of coming back to what Da Vinci will see. Of course, the visor instrument's not going to observe in this optical bandpass. I think that's wise. We didn't know about this when that mission was being conceived, but the visor instrument will not just have one photometric band, it'll have 3 to help disentangle cloud opacity variations, scattered light effects, and so that will actually make it significantly more robust at mitigating the challenges we saw, and it will allow it to back out subtle emissivity variations that are at 1 micron that are due to surface compositional differences. So I think that was a good design choice. I think it would be awesome in the future to have a mission that did use this optical window to the surface of Venus, but we'll just have to wait and see. All right. So that brings us to part 3 here, where we're going to shift gears one more time and talk about the ongoing hunt for rocky exoplanet atmospheres with the James Webb Space Telescope and how that gets us one step closer to in the search for life beyond the solar system. So the James Webb Space Telescope is extremely powerful for all types of astronomy, due in part thanks to its broad wavelength coverage from the near-infrared, about 1 micron all the way to about 30 microns, and also its large collecting area. It's a 6.5 meter space telescope, and it's sort of actively revolutionizing astronomy sort of day by day and year by year. It was supposed to have a 5-year original lifetime. Now NASA and the operators at Space Telescope Science Institute expect it to last at least 20 years due to its amazing launch and efficient use of propellant. So that's fantastic. It's super exciting. And its broad wavelength coverage enables it to do spectroscopy and disentangle the atomic and molecular species in the cosmos of all the objects it's looking at, and in particular, the atmospheres of transiting exoplanets is sort of the powerhouse of JWST for exoplanets. And this has been incredibly exciting and successful so far. Just as an example of this, here I'm showing the transmission spectrum, or the wavelength-dependent radius of this hot Jupiter exoplanet WASP-107b. Nothing particularly too interesting that I want to say about WASP-107 other than to point out this sort of rich spectrum filled with molecular absorption from water in the near-infrared here around 1 microns over to carbon dioxide features here at 2.7 and 4.3 microns, in this small but statistically significant detection of sulfur dioxide here around 4 microns. They also see a sulfur dioxide feature just past 7 microns. So this just sort of molecular census of giant planet atmospheres has been amazing already in just the first few years of JWST operation, and is sort of working, the community is working to build like a census of the types of molecules and chemistry we see across a broad range of planet parameters. Naturally, we want to use these techniques to study potentially habitable exoplanets, small Earth-like exoplanets. But I would say that we're at the humble beginnings of that venture. Small planet atmospheric characterization just must begin by just simply detecting the presence of an atmosphere around these small planets. And for now, geometric biases are strongly favoring the detection and follow-up study of small planets around small M-dwarf stars. So current technology means, we can only sort of do this type of characterization, or hope to do it, with the small Earth-sized planets around the very smallest of stars, where they're blocking a larger portion of that star's light when they transit in front of it, and they transit frequently due to their short orbital periods. This gives us sort of a bias in favor of studying these targets. But fortunately, most stars are M-dwarfs. So 76% of stars are M-dwarf stars. So there's a lot of targets to work with. And NASA missions and other ESA missions have been extremely successful at finding small planets around these small stars. So we know there are Earth-sized planets around the M-dwarf stars in the solar neighborhood. But the M-dwarf stars have extremely high radiation environments. They produce elevated high-energy XUV radiation. They flare frequently, and they have strong stellar winds relative to sun-like stars. And all of these factors drive vigorous atmospheric escape, or they all increase the rates of escape and threaten the survivability of atmospheres on M-dwarf planets. So I like to think about this sort of conflict between this M-dwarf opportunity that the field has been talking about for a decade, where we have this bias, this opportunity to study these targets at this time, but also this M-dwarf peril, the sort of high-energy environment that these planets are found in that threaten the ability for the atmospheres to persist. So we simply want to know whether rocky planets around M-dwarfs have atmospheres. And that kind of brings us to this cosmic shoreline concept that David Catling and Kevin Zonley worked on and published in their 2017 paper. The cosmic shoreline is a conceptual line that separates bodies with and without atmospheres in the solar system. So here we just have the solar system bodies, Mercury, Mars, Venus and Earth, so those in a strange order. But and the cosmic shoreline sort of divides these planets, but also the small bodies in the solar system sort of fall on this atmosphere's less likely side. And so the way to think about this is on the y-axis we have intensity of light, amount of light received by the planet, or total cumulative XUV flux received on the planets plotted here. You can think about it as the increasing likelihood that the atmosphere is lost due to atmospheric escape. And we have escape velocity on the x-axis, which you can think about as just the increasing likelihood that the atmosphere is retained. And the cosmic shoreline is this balancing act between the two, where on one side we have planets without atmospheres here, they've been lost, and on the other side we have planets with atmospheres. So wouldn't it be great if we could use this as a target selection metric? If we were really confident where this line was, well, we could just put exoplanets on it like are done here, and we'd know which have atmospheres and which don't. But nature's not so simple, and what happens in the solar system may not apply directly to each exoplanet system. So we really have to go out and test this hypothesis. So it's really a nice hypothesis to test and figure out the sort of functional form, or where is the cosmic shoreline in these M-dwarf systems where XUV radiation is so intense relative to sort of Earth-like planets at sort of habitable distances around sun-like stars. And so the Space Telescope Science Institute that operates JWST is devoting 500 hours of additional telescope time that the director has say over how that's used to study the planets in orange here, to search for atmospheres on these planets and determine sort of whether they have atmospheres or not, to sort of empirically put constraints on the location of the cosmic shoreline in these M-dwarf systems that we have this opportunity to study. In addition to the Cosmic Shoreline program, I'm extremely excited about this program charting the cosmic shoreline that I lead with my colleague Kevin Stevenson and our team, which we're searching for atmospheres on additional planets here, on pairs of planets in 3 different systems. So this is 6 exoplanets in 3 different systems, and we're trying to leverage the fact that planets in the same system will have a shared stellar evolutionary history. So to reduce scatter that we kind of expect to be on this cosmic shoreline concept, we expect that differing internal planet compositions, different stellar evolutionary histories, sort of ought to produce some amount of scatter to this relationship that may make it difficult to test in a population that across all the different exoplanets, but each individual system may have sort of a cleaner relationship like we see in the solar system. And so we think multi-planet systems may help in that way. It'll also help us reduce systematics and contaminating effects that happen from the star. By having 2 planets transiting in front of that star, we learn more about the star and can refine our interpretations and search for atmospheres better. And so this program is just getting underway, so I don't have any exciting results to show just yet. We're accumulating data sort of day by day as we go here, and I'm hoping that over the next year, 2 years, we'll be able to publish some exciting results and comment on the prevalence of atmospheres on these targets around M dwarfs. But sort of looking beyond the cosmic shoreline, I think there's some really awesome implications of testing this science case. So if some M-dwarf planets are found to have atmospheres, then that's great. This has been a great target selection, down selection, and we can begin to study their atmospheres in more detail. We can try to understand the habitability and even search for signs of life if we find that planets in the habitable zones of M-dwarfs do have atmospheres. But if none or most planets around M-dwarfs just aren't found to have atmospheres, then, well, this is a sort of a limiting case, but then the search for life around other types of stars becomes even more critical as part of our search for life beyond the solar system. And studying the atmospheres of planets around F, G, and K dwarfs is going to be the task of NASA's next generation flagship telescope, the Habitable Worlds Observatory. And so I think what we find on rocky planets around M dwarfs over the next 5 to 10 years, I think is going to shape the search for life on exoplanets for decades to come. Kind of contextualize the prevalence of life in the universe, just based on the sheer number of M dwarfs that are out there. All right. So that brings us to the end here. So to conclude, kind of loosely tie everything together here, we talked about the Rosetta mission and our efforts to refine the D/H ratio of Comet 67P. Just sort of conclude with this idea that confounding factors like the dust cycle on the comet that bias individual analyses can also bias how results contribute to sort of a broader population analysis or the broader interpretation that we're intending to make from a single measurement. I think that's an important one to take away for, say, like the JWST studies of the cosmic shoreline. Make sure that we're not too biased at an individual level so that our greater understandings of the population aren't also biased. We talked about the Da Vinci mission and how the imaging with VISR and Vendy will be used to distinguish different surface compositions, and how upcoming Venus missions will unlock the secrets of Venus's past and present to help us understand rocky planet evolution. And then finally, we talked about JWST's search for rocky exoplanet atmospheres and this cosmic shoreline community hypothesis test that, like the habitable zone concept, frames a local result here in the solar system as a hypothesis that we can test in the exoplanet data to generalize our understanding of planetary science. So with that, I thank you for sticking around to the end and take any questions.
All right, thanks so much, Jake. So just a couple of things while you're thinking of questions. As I mentioned, Jake is based here in West Seattle, so if you didn't have a chance to chat with him today, he's on campus like semi-regularly, so I'm sure we could set something up. But also, if you can't wait, we do have liquefaction after this. We'll be there, so feel free to drop by. So, any questions?
Thank you for that talk, Will. It was super interesting. I was just curious, for the imaging systems that people put on the missions, do they do analog studies on kind of broad scale? Like, do they put them in a plane and fly over a lava flow and see what they can see? Do people do those types of experiments?
That's a great question. That is something that different mission teams have done. I think the Da Vinci team may be planning something like that as kind of a next step, but not something that I am aware has happened yet. I'm familiar with colleagues who work on the Dragonfly mission, and they have done some analog tests, flight simulation tests, in sort of dune desert regions. So yeah, I think that is definitely something that is a good demonstration of capability.
Thanks.
Thanks, Jake. That was great. Just thinking about the sphere that's dropping down, I just wanted maybe a clarification. As you drop down, your field of view is going to change, right? So what you see at the top versus what you see maybe halfway down, how does that sort of factor into your final calculations?
Yeah, that's a great point. Definitely, we'll only have the lower most measurements for the smallest region. And so, one, that will be the region most well studied for sure from the imaging, but that's also partially why we use the sort of minimum number of images, just to sort of crudely account for the fact that it won't be possible to use imaging just from the top to the bottom because of possibly different, like wiggling and things that will happen. Not a technical term, but you know what I'm saying. But yeah, great question. I think it'll be challenging to just map any one place, but we might get lucky and have that the region it lands on hopefully will stay in frame for the whole descent.
Awesome, thank you.
Oh, that is such a good question, and I wish I knew that off the top of my head. I think like on the order of hours. It's not, at most, yeah, it's just not going to last very long. Unfortunately, I think, yeah, we all would want it to last a long time. And I think it kind of reminds me of the DART spacecraft, which is another APL mission, but smashing into an asteroid. I think that it's strange to put so much effort into a mission that sort of ends so quickly. But if it can accomplish all the science objectives in that time frame, I think it meets the objectives, and even if it comes to sort of a quick end.
From what I remember, it'll just keep sending back data from the surface until it sort of melts, right?
Yeah, they'll take data as long as they possibly can.
Could you review the evidence again that there might have been oceans on Venus? I'm a geologist, the first time I've ever heard that.
Yeah, so, I mean, this is definitely more in Josh's wheelhouse than mine, but people have modeled the climate of an early Venus before it lost water, and under certain circumstances, and I can't remember all the details of those specific circumstances, you could have bodies of water on the surface, but I think it's an active area of research, and it's not, what's known is that Venus lost water, but whether that water was ever in liquid phase at the surface is a significantly more contentious question.
How do you know Venus lost water?
So one of the lines of evidence is the extreme D to H ratio, exceeding any solar system object, way above the sort of formation materials. If Earth's water is consistent with, say, the Jupiter family comets, the D to H ratio of Venus is like enhanced by about a factor of 100, I believe.
Just one thing to add to that. I mean, a lot of the back and forth is models don't agree on early habitability. The one really interesting data point that we have, I think, is observations of the surface through these near-infrared windows showing like the emissivity of the crust is consistent with something granitic. It's different from what you'd expect from basaltic plains. And so that region, Alpha Reggio, which looks like there's a potential granitic crust, is exactly where they're dropping this probe to really characterize. Is it granitic, right? Because presumably you needed surface liquid water to create a lot of granite, is kind of the argument. Yeah. Other questions?
Yeah, thank you, Josh.
Hi, cool talk. I'm not an astronomer or astrobio person. I'm a geologist, but I'm curious about the third kind of subject that you were talking about in the cosmic shoreline.
Yeah.
You mentioned this kind of technological sweet spot that allows you to test this hypothesis on M dwarfs, but what kind of improvements, I guess, would need to be made to be able to test, say, like, you don't find any atmospheres for the M dwarf, like, exoplanets, like, what needs to develop for you to be able to test this on other types of stars?
Yeah, that's a great question. So the key thing, I think, is that the technique of a transiting planet, we take advantage of the unique geometry. It eclipses the planet, eclipses the star, blocks a little bit of the light. The amount of light it blocks is relatively large for an Earth-like planet around a small M-dwarf star. Stars that are like Jupiter size to 3 times Jupiter size, or 3 to 4 or 5 times. Anyway, that technique kind of breaks down in terms of being able to do precise atmospheric characterization for Earth-like planets around Sun-like stars, just because it's an area of overlap problem, and you end up needing really, really high precisions to do it. So instead, we need to use techniques that don't use the transit technique. And so this is what the Habitable Worlds Observatory will use. It'll use a coronagraph instrument to block the light from the star, and be able to detect the faint light reflected off of planets orbiting around it. So think more like the pale blue dot, rather than sort of an indirect inference that the planet is there because it's blocking light. We're going to be able to observe light reflected right off the planet. And so this will have a different sort of sweet spot in terms of the types of planets it'll be sensitive to. Those further away from the star will be more the focus of the study, just because you don't, by blocking the star's light, there's a certain inner working angle that you can't see planets within that. But nonetheless, that is sort of going to be the premier technique in the future to study small planets, or all exoplanets that they don't have to transit, so that's a benefit. So we can sort of open up our search of exoplanets around all the different stars in the solar neighborhood, and in particular go after more sun-like stars, FG and K dwarfs.
Cool, thank you.
Thank you. Wonderful talk there. I was curious in regards to the M-dwarfs and the cosmic shoreline. I was a little concerned. Because of the ideal conditions to get these transit-like spectroscopy bits from the planets orbiting M-dwarfs, we kind of dodge the cosmic shoreline zone for Earth-sized planets, I think, if I'm remembering right.
Oh, from the figure?
Yeah. Yes.
Yeah.
Mostly because they're so close, going around so fast. They also happen to be extremely irradiated by the M-dwarf.
Mm-hmm.
And it concerns me a little bit that can't we do this for K-class as well? I could swear transit orbits were still viable for K-class.
So definitely, we can detect planets in transit around K dwarfs and G dwarfs. I think when it comes to small planets, our detection, completeness, our ability to find planets confidently is a much more complete search around M dwarfs, but also the ability to sense the atmosphere is another layer of precision needed on top of just the detection of the planet. So the subtle absorption from just the molecules in the atmosphere is really what doesn't scale favorably into K dwarfs. Even into early M dwarfs, it becomes very difficult to do. But so there is kind of this transit bias towards highly irradiated planets too, which is kind of means most of the targets are on the wrong side of the shoreline. And so we do have 2 techniques to search for atmospheres for transiting planets that are being used with JWST. One is the transit technique, where we're looking for absorption in the planet's atmosphere. The other is at secondary eclipse, when the planet passes behind the star. There we're looking at the day side of the planet, where a measurement of, a deep eclipse depth where we get a strong measurement of the signal implies a very hot planet. And so there's this sort of logic that's used is that an airless planet can't redistribute heat to its night side, so its day side is sort of maximally hot. That technique especially is well suited for planets on the wrong side of the shoreline. So at least the JWST program that I'm engaged in right now is searching slightly more temperate planets. It scales better to cooler planets into the habitable zone than thermal emission does. But there's no doubt that it's a challenge. It's an extreme challenge to sort of push onto the atmosphere's side of the shoreline with current technology. And perhaps better suited for future observations in direct imaging, where they're sort of have the bias in the other way and towards planets further away from the star.
Okay, thank you.
Maybe if there's one last really quick question. All right, well, if not, let's thank Jake again. Liquefaction's happening now.